Welcome back to I'm Finally Reading My Brother's Book. I'm Clay Bascom, and yes, this is episode 2, but we're finally diving into chapter 1 of my brother's book, On the Inside of a Marble. If you're new here, my brother, Dr. Gavin Bascom, is a theoretical chemist with a brain full of cosmos, and I've been avoiding reading his very dense book for years, but I'm finally doing it, one chapter at a time. And this week, we actually begin. In chapter 1, Gavin starts big and tries to contextualize the entire universe. The past is at the edge, now is at the center, and we are somewhere in between. It's disorienting, it's mind-bending, and it raises more questions than it answers. Let's get into it. Here's episode 2, chapter 1. Hello, Gavin. How's it going?
It's going pretty well.
All right, well, let's just dive right in. So let's start off by asking you, why did you feel the need to write this book?
Yeah, that's a lot. There's probably not a super short answer to that. But so I wrote this book it was about 10 years ago now, and a lot of the core ideas were developed when I was writing my dissertation, which was another 6 years before that. So, but I think the better and the more approachable answer, rather than maybe I had all these ideas and all this to say about the thing, really I had been on a mad sprint to come up with some of the best ideas I could come up with since I was in grad school. And when I got into my postdoc and I was like making my way towards the end of my postdoc and realizing that maybe I didn't want to be in academia and like maybe I don't need to like be on this mad sprint to have the best ideas in the world, because it's like if you're a professor you have to have all the best ideas, right? You have to like have them to your name
Publish.
and publish them. And so then I had this sort of crisis moment where I'm like, you know what? I have all these crazy ideas I've been working on. And I had all these books in the back of my head I was going to read. And I'm like, you know what? I'm probably not going to write any of those books. I'll just write this one book and that'll be it. And I started with this idea that I had about the way that we measure time, because that's what I was studying. And then I was just very, very interested in cosmos and the other things. I had this aha moment. I was living in New York and I was sitting in my apartment, and I saw this picture, which is now the cover of the book. Luckily, it was open source and I could use it, but where they depicted this idea that I've been struggling with, where like time, you can map out time linearly, spatially away from you. And they do that with the cosmos. And then all of a sudden it just clicked. Oh no. Cause somebody in the comics was like, oh, that's dumb. That's not how it really is. And I was like, well, it's not, it is how it really is. And it isn't how it really is. And that distinction is what's so interesting. And that's kind of the core idea that sparked the book.
Cool. Why don't you tell me a little bit about just sort of the accessibility of the book, because I got to tell you, the assumption of knowledge that you made of the reader when you wrote this book is quite high. And so I think, like, when I have tried to read this book a couple of times, and each time it was like I had to you have to stop and go back and be like, he assumes I know what that is, and I don't know what that is. Let me look this up and try to understand it. So like, I will say there's that barrier to entry with this book, but I will say if you have a digital copy now, real easy to select, search Google. There's a couple of things that popped up. At one point I was reading, and then all of a sudden you're talking about Maxwell's demon, and I'm like, I just don't know thermodynamics well enough to know what the hell that is. And so it just seemed like left field. Suddenly you're talking about a demon. I'm like, what's
It's an
happening?
old physics problem.
Yeah.
But yeah, no, totally. And I like you're right, it is dense and but it is short. The one
Yeah.
thing
It's
not
short.
super long.
No,
Like you could read the first chapter in 15, 20 minutes, and you could probably read it over and over again if you really needed to, in not that much time. But yeah, and it goes back to this idea that I was in academia and I was kind of flexing, and it's kind of like the powerlifting of writing and like of thinking. But because there's a real beauty in that. Like there's a real, like when you push yourself to think hard about things, they start to click in ways that they wouldn't otherwise. And a lot of it comes back to is that the people who study this stuff, they generally do it in math speak. And I am good enough to sort of read it and understand the math, but I'm not good enough to really formulate it and write it down myself. So in a lot of ways, this was me struggling with how do I use the skills that I have to make comments on these topics. And I also was like really influenced by some philosophy that I was reading, especially Dan Dennett and some other popular philosophers, and also some popular science books about quantum mechanics and cosmology at the time. Sean Carroll um, and some others that I talk about in the book. But like, so there's some flavor of this and some flavor of that. But there are through lines, and they're not that hard to understand. So anyway, that's part of why we're doing this podcast, right? Like I'm relishing the opportunity to go back and talk about how concepts are not that hard to understand, But you do have to so you got to put some effort.
Yeah, I think when you said they're not hard to understand, I think it's if you've already been thinking about these concepts and you have had years to get comfortable with them, I think you're trying to even stretch that a little bit. And so for the
Mhm.
layman, it's like, okay, I have to first come to grips with what most scientists already grasp and then try to contextualize that within like your insight, which is really, really
Yeah.
interesting. It definitely, stretches the mind trying to do it all at once. But you have some really good sort of exercises in the book. I liked
Did you do the first one?
I
Did you
have,
actually do it?
yeah, not this read through. I have in the past. I should have done it. I should have done it. So yeah, in the book, Gavin asks you to close your eyes and imagine slowly zooming out. Start with the room you're in, then I think you say the room, the house, the city, and just keep like slowly going out. And there is this interesting thing that happens that eventually, in the room you're in, you're in the room and you're looking at it from your perspective, and then almost immediately when you go to your house, you're looking at it from like a bird's eye view. At least that's how it happens with me. And then
Yeah,
it's like,
that's I would love to do this experiment, go and actually, see what people like when
yeah,
but, like, almost everybody eventually is looking at some, like, artist pic by the time they get to the universe, it's like an artist picture,
yeah, it's in like a
right? That's the
rendition,
point.
and yeah, basically kind of stretching of like what is reality and what we think of reality. But that ties us in pretty nicely to start getting into the chapter. Kind of what I wanted to do is give you my take, what I took away, sort of breaking different points down and stuff, and then have you kind of be like, no, it's actually
Yeah.
this, because I
Well,
do think there's
maybe
going to be a lot
before
of
we do
that.
that, one thing
Yeah.
after listening to the last episode, which was, obviously not very planned out, and, like, we were just kind of
What? I spent so many hours.
just chatting, but, like, there was one part in it where I said something wrong, and so I just wanna correct that, which was I
Feel
said
like
something to
we should have like this at the end of each podcast.
the
The last
addendum. Yeah, yeah, yeah,
podcast
yeah,
where
yeah.
I said,
I listened
uh,
to it again, and no, I just was talking fast and I just said it wrong. But basically, I said nobody in cosmology, nobody uses relativity, and that is not correct. They use it in everything, and it's a very key part of all of cosmology research and the way we think about the universe and how we measure it, and also. But anyway,
how
but
they integrated gravity, right?
well, yeah, and I guess the point I was trying to make was that there's a less often talked about effect of relativity, which is how like, when you measure infinity, it has to do with space-time curving and like stuff, which is not as often talked about.
Mm.
They talk about it in quantum gravity books and stuff like that, but it's not. So anyway, so I just wanna
Set the record
make
straight.
sure you don't
People
piss
do
anybody out there.
use special relativity when working on cosmos problems
Or just any when you measure a particle or when you talk to a satellite. When satellites talk to each other, they use it. They have to.
because
Yeah.
otherwise the time would be wrong. Um, all right, so I would say what I took away from this first chapter was you're kind of trying to give us the vision of why you kind of wrote the book in the first place, and not so much your personal life vision, but you kind of talk about it in your forward a little bit, and then towards the end of the chapter, which is basically that there's sort of a certain perspective that you got from working on things, and my understanding of that was that you understood certain things from quantum mechanics, that things get really, really weird when you get down to that level. You start working in probabilities rather than, realities. And then, but when we think of working in, normal, spaces or, much larger things, or, I don't know, with proteins, it's what you work with, right? Proteins, that when you kind of bring time into the equation, because you're taking snapshots, but you're trying to get an idea of how the proteins are binding and how they're twisting around and stuff, um, that you realize that you're running into a lot of the same weird things in quantum on a more macro scale. And that sort of led you down this path to sort of try to tie the two and understanding why, you know, certain truths about the quantum level, um, are also true about our normal reality. We just don't look at it the same way or something similar.
Yeah. 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 No, that's a good way to put it. And because like you said, I study proteins, I study how proteins fold, and I study how drugs bind to proteins, and especially DNA folding at the time when I was writing the book. Um, and but the way that we study it is we use the computer and we set up these equations that are sort of, okay approximations of the way that atoms move around. They're not even fully quantum mechanical because it would need too much compute to do that. There's a funny conundrum when you talk about how it can be applied or how it can be used, you're never directly watching. Like you're never directly like nobody thinks this is an actual protein, right? It's a representation of a protein. But even in working on my dissertation, like I realized like it's not even just that it's a representation of protein, it's that the steps between the time steps, you simulate at time t and then you go simulate at time t plus 1, even the movements between the time steps are not deterministic. They're not physical. They're probabilistic. And there's, in theory, you could write down equations that get you perfect, exact ways to like do that deterministic view of the universe where if you had all the information, you could like predict where everything else is going to be at a certain amount of time. But like, it's just not true. Like there's no framework out there that can accurately describe like exact positions and momentums of particles for anything that's even a very large bath of molecules, as opposed to like just a single individual particle. So yes, the correlates between where you have to abandon determinism and start to think about probability, that was the core of the book.
Yeah.
And there's a correlate to the Schrodinger equation in my world, which was a weird thing to realize for me, but
Yeah, it's really cool. Okay, so yeah, so that was kind of the gist of the book that I got. But I went through and wrote down some different points that I wanted to hit that I thought were really interesting and kind of necessary ideas to understand. Because I feel like most of what this chapter was you kind of laying the groundwork for saying, hey, I'm going to get into some really weird, interesting stuff, but you kind of need to have this perspective in order to move forward, if I'm understanding correctly. And so let's build that. Let's help these people listening build this context that they need.
One of the core ideas of the book, and it's easy to summarize the first chapter, is that there are these sort of three ways that we interact with our reality that we think of as all parts of the same thing, continuous spectrum of the different things, right? And one is the instantaneous perspective of how things look. When you look and you see things far away, they appear a very particular way, but it's an instantaneous static thing. That's one part of reality. The second is how things feel. If you go and you look at it from different angles and you touch it and you understand it and you come to understand something, but still sort of instantaneous, right? This idea of when I pick up an object, I know that the object has certain shape and feel to it, and it's not changing with time. Then there's the third one, which is the narrative. It's there something happened at time A, and then something happened at time B, and we can traverse that narrative. However, the reality is that those three things are not separate, and that we have to understand them separately, though. But when you look out at the horizon, you're getting some version of that narrative, but in a perspective distorted way. And so the question is there a time perspective distortion in the same way that there's a space perspective distortion?
Oh, that makes sense.
Yeah. And that's kind of the big takeaway. And is that time perspective distortion, is that relativity? Is that because of relativity? Because it's different for every observer.
I did watch a YouTube video once, maybe I'll link it in the show notes if I can find it again, where a guy did his best to make a visual representation of gravity. And it was really interesting. And he talked about how, on the fourth dimension, when you add in time, when you're walking in a straight line, do it justice, but when you're walking in a straight line, the reason why the world's become a sphere is it'll make it to the top of the
yeah
basically.
We talked about this in the first episode. That when space-time is bending is when or starts curving is when you sort of think you're moving in a straight line, but you're actually
moving this way,
in a curved path through space.
And so it's a really good. It was one of the best for me because we've all seen the sheet experiment but the sheet representation where you take a ball and you put it on a sheet and it bends it, and it's like, oh, that's gravity. That's actually not a very good way of understanding it because
it's a good way of telling you the potential energy of gravity.
Sure.
But what Einstein really said, which was really is hard to understand, was that there is no potential. Gravity is not a force.
Right.
Gravity is just curved space-time.
Yeah,
which I don't know. How do you understand that?
Blows my mind.
And if you're gonna think of the whole system concurrently and consistently, then you need to think about the whole history of the universe and why space-time is curved around things with mass.
So why is it
hard.
Is that
hard to think about? I don't know.
Is that the ending of your book?
No, I don't. No, we'll get there.
Yeah, so I wanted to talk about one of the more interesting parts is relativity, uncertainty, and completeness. You talk about, Einstein's relativity, Heisenberg's uncertainty principle, Gödel's incompleteness theorem, all point to the limitations of understanding a fully deterministic, linear narrative of cosmos. In the last
Yeah,
episode, I called it the
yeah.
thinking sequentially. Yeah, so if you go to the
Right, right, right,
history,
right, right.
explain a little bit about what each one of those are and how that uh, sort of should change our perspective.
Okay, and we talked a little bit about this earlier, like this idea that the hallmark of the early history and thinking and the way that you think about everything and what you observe and what your reality is usually some narrative based thing. That first I got up and then I walked over here and then I did that,
Uh-huh.
and like, the sort of truly revolutionary ideas of the 20th century in math and physics were about what we can't know as opposed to what we can know, what you can determine. And so there's this deterministic view, or like there's a better word for it, a view where you can break everything down into deterministic laws, where if you had all the information you could predict anything, any outcome,
Yeah, it's a brain in the vat
right?
sort of thing when you're talking about consciousness, right? If you could
Well,
control.
yeah, I mean, that's a slightly different thought experiment. This is more just if I had all the compute power in the world, or if I could write down every position of every atom and then like solve Newton's equations, then I could tell you the position of a water droplet on the other side of the planet in 2 years from now, which is actually not true. Like if we could do that, we would then like weather people would be better
Yeah, well,
at what they do.
the thought experiment goes like, if you could actually compute all of the knowledge of the universe, you knew where everything was when it started, and then you could use the laws of physics to basically predict everything that's going to happen. And it's why some people believe that like, free will isn't real, that this the deterministic
Yeah,
view of the world.
right.
Um, yeah, whereas these three things, Einstein's relativity, Heisenberg's uncertainty principle, and Gödel's incompleteness theorem, sort of dispel that a little bit.
Yeah, it's a shift. In my mind, it's a shift in the narrative history of science where we start thinking more about what we can know. So, and I think the better, all of them are different flavors of the same thing, but Gödel's incompleteness theorem is one of my favorites, where there had been this outstanding thing in mathematics where if anybody could just solve these last couple of principles, there's I think it was Bertrand Russell set up had this whole book with all these axioms, and he had like completed math. Like everything was self-consistent, it was all proved, except for these couple of like weird little theorems. And if you just solve this last one, and he said it, he like made a prize or something where like whoever could solve it was gonna, get a prize in mathematics. And then Gödel writes this little paper where he just shows that it's impossible to do that. And basically, what he said is any system that is complex enough to represent itself cannot be simultaneously consistent and complete. So you cannot finish the representation and have it fully explain everything inside the system and still be self consistent. Why? Because I can write down little representations that are not self consistent. Like,
Yeah.
it's very easy to do that. So as long as the semiotics have enough capacity to describe everything in the system, they can describe something that's not true for someone else. And that is almost exactly what Einstein is saying, right? If I write down the position of somebody, or I take a measurement and I say, okay, this is how fast something's happening, this is how hot something is, that will depend on whether I'm in the same reference frame as someone else. So no matter what you do, you cannot describe the entire system and be consistent with everyone else's worldview in that system.
Yeah.
So that's a huge moment where we start to understand what we can't understand about these things.
Yeah, and like, didn't it dispel the idea that we could have a fully formed, perfect math to describe everything, right? I forget the.
Yeah,
Yeah.
yeah, and that's where in the Gödel's incompleteness was about math, and then Heisenberg is about, well, you can't know position and momentum at the same time. And whereas Einstein was more of a macroscopic thing, but it's more just about like the observers. If people are in different reference frames, then they can't you can't know what happened first. Sometimes it's really hard to spell that out. Yeah, which has really far reaching implications for how we think about these things.
Yeah, yeah. Okay, so kind of piggybacking on that, the other big thing in your book that I got this time that the previous times I've read it, I definitely went over my head, where you talk about kind of language and symbols and how math is set up in order to explain the universe in an interesting way. And I'll use your pot lid example that you use in the
Yeah.
book. So basically, you have a bunch of different pots, and they're all different sizes, but they all have different shapes and things, and used for different things. But all of the lids are unified; they're all the same. You would say that the pot lids are promiscuous, or functionally promiscuous, right?
Yeah.
So basically, you can use the different pot lids on different pots interchangeably, and that's totally fine. So if you can also apply that to language, meaning that one word can mean multiple different things, right? Apple can mean New York, it can mean thing you eat, it can mean, a couple different things. That's a symbol that can be
Mm.
promiscuous, means it can mean different things depending on the context. And that's really useful in language and something that's, good. So first I have to understand that, okay, what that promiscuous, functional promiscuous and semiotically promiscuous means. And they also talk about drift, which we've heard about drift in language.
Yeah.
That's where over time a word starts to mean something different. So if you were to take someone from 100 years ago and drop them in today's society, they'd have a real hard time, even if they spoke the quote unquote English. Would be
Mm.
very different, especially depending on where they are. And so you take those two ideas and you make a really interesting point that I really want you to kind of try to explain a little bit better. You basically say that when it comes to the laws of physics, which is a type of language that uses, semiotic promiscuity, rules of physics are like that, meaning that like they can be functionally interchangeable, that basically as you travel in time and space and in temperature, that semiotic drift kicks in and basically results in the reason why the universe, like why quantum mechanics is the way it is, and why the cosmos has a nonlinear history is because of this.
Well, I don't know if I wouldn't go as far as to say it's why. It's more, going back to the powerlifting thing, it's like me doing powerlifting, trying to sort of understand if there's a place where the language breaks down so that we can start to understand why the universe gets hotter as you go further out. Like that to me, that's a big question that I'm like struggling with here.
Hmm.
Like because we measure it in a very particular way, but it just doesn't make any sense. Like,
Yeah.
so then there's this idea, but and then you start grappling with the timescales. So going back to the thing we talked about earlier, where you have this invariant universe where you look at a cube and it has 90-degree right angles when you see it up close. From very far away, it looks more and more like a ball, and eventually it becomes a point. Atoms are hard to look at. They're
Yeah,
really
sure.
hard to look at. This concept that we can look at them because everything is made up of them is actually kind of a weird misnomer. You can measure them by doing an absurd amount of smoothing out forces or very high energies. So we can only look at atoms really by applying very, very hard forces to get them to split up and do interesting things. And what we really could look at is light, which is a different thing. And light is really just the atoms moving in the way that they jiggle a little tiny bit differently than they would otherwise. And I think we'll get into that in a different chapter. But so this idea of this semiotic drift and semiotic principle, so it's easy for us to understand why if I try to read a book in Old English or Middle English, I can't read it anymore because it just changes. Like the language isn't the same. It wasn't developed for that frame anymore. The language that we use of now,
Hmm.
and I can take measurement by having my clock turn on, so I can say, okay, Adam was in position 1 now, and in position 2 1 second later. That language is mostly developed for macroscopic objects and ideas. And so as we start to apply it to really small things or things that are really, really far away, it just probably doesn't
Makes
work
sense
anymore.
anymore. Okay.
Like it
That
just
was
doesn't
kind of
make
the
sense
point.
anymore.
Right.
And that is, in my mind, that is relativity. That is why the cosmic horizon looks something different.
Right.
Now
And
I've
so
gone all the way
that's
back to
why
say why, but yeah.
and so that's why we have to make new laws, right? And that kind of ties in with another part of the book, or in the same chapter. You're talking about cold versus hot physics and how,
Yeah.
basically, I guess the cold physics people are looked down on by the hot physics people because they think that the hot physics people are going, hey, we're having to write we're changing the laws of physics over here. We have to write new laws of physics because things get so
Yeah.
crazy
Yeah.
the hotter you get. Whereas cold laws of physics, it's like, well, no, that's deterministic. That should be easy.
But what they're actually doing is proving the non-locality of the universe, which is to me an even more fundamental and more mysterious principle. It goes back to, and this is another thing I talk about a lot in the chapter. We have in the same way we have a bias towards narratives, we also have a bias towards hierarchies. And we want everything to fit in a nice, neat little hierarchical box where we say, forces give rise to atoms, give rise to molecules, and molecules give rise to whatever, and that gives rise to chemistry, and chemistry gives rise, so the physics fits. Chemistry is just a special case of physics, and biology is just a special case of chemistry. And that's always bothered me in a really big way, because the actual meaningful observations for each of those things were functional throughout history and throughout time. So the thought that the reason the hot physics guys are a little bit entitled is because they think we're uncovering the foundational laws of the universe. Like we're getting more and more, but that to me is kind of anthropocentric too, because or it's this hierarchical centrism where, yeah, but what is the actual predictive power that comes out of that? The predictive power that we have now is very limited from anything quantum and smaller.
Yeah.
And I'm not saying that there aren't, but there are some real serious things that came out of that, like fMRI and all sorts of things that are really useful. But it's the utility is becoming less and less so compared to advances in chemistry or biology or computation, which are, completely swarming the rest of the fields in terms of the scope and size of the funding and everything else. Yeah. And then whereas the cold physics guys are over here proving that the underlying assumptions of that hierarchical pyramid are wrong. By just because there are still people out there arguing that this is quantum mechanics is all just kind of like you're just not seeing there's hidden variables. They're just in there somewhere. You're just not seeing them. And don't worry, the universe is deterministic and everything is deterministic. It would all make sense if we just had all the information. That's why I like the cold physics people, because they're still quietly running these experiments that are extremely hard to run, where you have to measure things across large distances without having to spin up huge particle colliders to do it.
Yeah. I was good to just to clarify. Yeah, when you're talking about hot physicists, are the people running the Hadron Collider, right? They're smashing particles into each other, through the speed of light in order to measure stuff and try to get the weight of the Higgs boson.
Yeah. The standard model, right? Like just break it apart and then look at the way that the things break apart, and then you can make predictions about what's going to happen when things are broken at high energies. Basically, you can just measure, this particle shot off in this direction as opposed to that one, and then so therefore it must have this force on it or whatever.
All right, cool. Well, it was an interesting read, I'll tell you. I actually enjoyed it the most this time out of any others, as I was taking notes and stuff. I think that's the other problem, is in the past I tried to read it not passively, but it was like I wasn't approaching it with the respect it deserved. But what
I appreciate that.
Yeah.
I appreciate that.
Yeah. So, what do you think is the hardest concept in chapter 1 to accept?
Yeah,
Or to
I think
understand?
I think it's this. A lot of people don't understand that when you measure something very far away, when you take you're essentially taking a picture, and I think you said at the beginning of the podcast, things that are far away are hot, but actually it's more that things that are measured at any point now, at any instantaneous point with smaller and smaller instantaneity, which means more and more precise measurements between the light sources. Those are the things that are hot and far away. But you measure them at any point in space. So which there's a statement in the book, which is the Big Bang is happening everywhere now, but it's happening at very small spaces between atoms, basically. And that is such a different view than the string theory views and all these other views, which is all deterministic, where you have to break the atoms down into pieces. And we'll get into it later, but the book is really about trying to let go of that view and say, no, maybe we need to look over our shoulder a little bit and understand the things coming from big up far away, and how there might be some sort of unintentional semiotic drift between the way that we talk about atoms and the way that we talk about the cosmos. And if you're going to have a quantum gravity, it's not going to be because you wrote down equations that somehow smooth out gravitational problems at the Big Bang. It's because you understand that there is no beginning and there is no end, and there's just the observable beginning.
But we're definitely inside of a black hole, right? Hey,
I don't know.
I think we are. I think that should just be canon now.
Yeah, sure. We'll just refer to it that way.
All right. Well, this has been fun. I'm excited for chapter 2. I've actually never made it that far. I have finished chapter. I think I'd almost finished chapter 1 quite a few times. This was good. I actually finished chapter 1. Fully read the 20 pages. It took me a while to make it through, but it was it was very interesting. I only had
All
to look
right.
up,
Any tips
a
for
couple of
people?
things. Yeah, I would say if you can get your hand on a digital copy, because then you can just select what you're not understanding and hit Google search. Click Google search. That saves me a lot of time because I'd be like, I don't, what is this? Like the funniest one was the one where I was like, because this book can be when you trail, your thoughts start to trail off. It happens a lot because they're like,
Yeah.
as soon as you hit something you don't understand, your brain automatically goes, you know, what am I gonna have for dinner? And so I was doing that a little bit, and then all of a sudden I read Maxwell's Demon. I'm like, I didn't know we were going to be getting into angels and demons. Woo, let's do it. But yeah, apparently that's a thought experiment about thermodynamics. So I looked that up. That was
Yeah.
really interesting. I had never, I
Do you
had,
know I met the guy who solved Maxwell's Demon.
really?
It was an outstanding problem since for
Well,
forever,
yeah, I
which
think it was
to really quickly
1867 or something was when it
yeah,
was
yeah, yeah.
originally.
I guess to really quickly summarize it, there's this thought experiment. Say you have two baths of gas, and they're separated by a small membrane, and one is or they're the same temperature on each side. If there's a little demon that stands on the gate and it waits until an air molecule comes towards it and measures the energy that it has, it can decide, okay, if this is hot or cold compared to the rest of the temperature, I can raise the gate and let the molecule through. So now if you choose to only let hot molecules through, you can actually heat up one side and cool down the other side.
Mhm.
So there's this interesting
But that
conundrum, and
should break the laws of physics, right?
it does break the law of thermodynamics by saying without any heat bath or external source, I can heat up one side or cool down one side just with enough information about the particles in the thing. And it was solved by a guy named Jarzynski, who's now at the University of Maryland. And I was interviewing for a position there, and I met him, and I was looking at his recent research, and I realized he had solved it. And the answer is that there is a certain amount of heat associated with the information that you would collect from that atom. So if you account for the heat that dissipates when you collect that atom, it no longer right. So in order to write down the 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 velocity, which is what you would need to decide which ones to let through and which ones to not let through, you have to take out energy of the system, and it can be shown rigorously that that is the same amount of energy that is needed to conserve the thermodynamics in that
That's
problem.
crazy. I still don't
Yeah,
fully understand when people talk about information. Like,
it's a
what?
core concept in the book.
Yeah. So we'll get to
And
it.
so we should talk about it, but because actually one of the only citations I've had of the book, they summarize it by being, well, Gavin thinks everything is information. The universe is really just information, and if you can write down all the information, then it'll all be solved. That's not quite true, and I do think it's part of the modern era.
Cool,
Um,
cool. All right. Well, thanks for coming. See you next time. Big gulps, huh?
See you later. Oh, we need a better outro.